Hi everybody, welcome. My name is Dr. Mrs. Sabina N. Ude from the Department of Materials and Metallurgical Engineering here at the University of Nigeria. I'll be talking today on the properties of sprayed fabricated cerium-doped zinc sulphide films. Let's look at the experimental work. First, we had to prepare our substrates. We used glass substrates. These glass, they were cut into a required dimension of 7.5 by 2.5 by 0.1 cm. And we did a cycle of cleaning, including washing with distilled water, soaking with alcohol to get rid of any contaminant, and subsequently rinsing with distilled water. After that, precursors were used to form solution of this zinc sulphide, and the materials we use as our precursors to form the solutions were zinc chloride, the thiourea, and ammonium ferric sulfate anhydrous. After the mixture, solutions of 0%, 3%, and 5% cerium concentrations were made. So, because we've known that the crystalline nature of this zinc sulphide comes in at any temperature above 400 degrees, these films were deposited at 450 degrees C using the different concentrations. The 0, whereby you don't have any cerium in it, and the 3% and the 5%. And consequently, the samples were labeled ZC0, ZC3, and ZC5 for the 0, 3, and 5% cerium concentrations. If you look at the first one was at 31.79 degrees, whereas the second one came in at 66.29 degrees. And for the 5% cerium, the 2 theta angle is also very close to what we saw in the 3% cerium. The first angle was at 31.81 degrees, whereas the second one corresponded to 66.31. You can see a little expansion of the angle between the two, the 3% and the 5%. And this what we found out here corresponds to, it's within the range of what we have seen in the literature for these 2 theta. And of course, the d-spacing, you have 2.8125. For 5%, you have 2.818 angstrom for the d-spacing. Now let's look at the optical properties. We measured absorbance against wavelength. From here, you can see that the undoped sample has a higher absorbance compared to the other 2 that were doped. And we also see that as you go up in wavelength, the absorbance of these 3 samples, as you go up in wavelength, the value of the absorbance falls. The three, they follow the same pattern, just that we see that the undoped sample has a higher absorbance compared to the doped sample. And even for the doped sample, the red light represents the 5% cerium, while the black line is for the 3% cerium. The 5% has a higher absorbance compared to the 3%. Now we're going over to reflectance. The reflectance is also, the graph is reflectance versus wavelength. As you look at it, the B line representing the undoped sample, the same trend, the reflectance goes reduces as the wavelength is increased, with the undoped sample having the highest reflectance. Again, the 3% cerium doped sample has the lowest value compared to the 3, with the 5% cerium being in the middle. And the third graph represents a graph of transmittance versus wavelength. Here we see that the transmittance increases with increase in wavelength. And we can see that the black line representing the 3% cerium has the highest transmittance compared to the other two, followed by the one that has 5% cerium. And of course, the undoped one has a lower transmittance. And we can see from the three graphs that the 3% cerium doped film has a better quality compared to the other ones. So doping with cerium enhances transmittance of the zinc sulphide films in visible and also near infrared regions, and as a result, these films could find application in optoelectronics and selective coating for solar cells and photonics. The first one represents the undoped film, and the B represents your 3% doped zinc sulphide, while the C, the one at the lower part of the screen, represents your 5% cerium. The film with the 3% cerium has a fine nano-flake surface morphology, while the film while the film with the 5% cerium contains some agglomerates of particles in their surface morphology, and this can be attributed to the dislodgement of atoms of the host matrix by the cerium ions, because you're substituting the cerium into the zinc sulphide matrix. So in conclusion, the cerium-doped zinc sulphide films were deposited on glass substrates using spray pyrolysis at a substrate temperature of 450 degrees C. The studies on morphological, structural, and optical properties were performed using the mentioned equipment before. And from the discussion of the results, we saw that the doped films exhibited a hexagonal wurtzite structure with 105 and 1112 orientation. Somebody might ask, why do we have four figures here? Because it's a hexagonal structure. And again, the film doped with 3% cerium showed the optimum characters of a high transparency within the visible region. So we recommend that cerium, among other metals, it's a good dopant for this zinc sulphide films. Several applications. Thank you.